So my name is Tommy. I didn't include an intro slide, but I'm going to be talking about my project here, which was using, like speech synthesis, and specifically, I did some work with speech synthesis in GANs. But before we get started, I'm from the U.S. I'm a data scientist for Expedia, and yeah, that's sort of my background. So speech synthesis, yeah, I guess not everyone really knows what it is. It's basically just like generating audio data that sounds like speech. And like a lot of really big name companies and organizations are working on speech synthesis, but they're usually just focusing on text-to-speech. But the results are actually like pretty amazing. They're not always reproducible, but they're pretty amazing. And so just to show you guys like how great they are, I'm going to try to play a demo. And it looks like we haven't tested the audio here, so maybe we'll get lucky. Oh yeah, okay. So for this first example, this comes from the Mila lab, and they use this model called Care to Wave.
About our horses, said the stately lady, that your recommendation would go a long way with.
Wait, can people hear this? Keep it closer. Okay, hold on. Let me try once more.
You have always been such a good advisor to us about our horses, said the stately lady, that your recommendation would go a long way with.
Yeah, so this one's sort of okay. The cool thing, though, is that this was like almost a complete end-to-end deep learning model. And it has like some fairly simple building blocks. But the models actually get better. So this is actually a famous model called WaveNet by Google, and a lot of you have maybe even heard some of their samples.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Yeah, so this one's like clearly a lot better. It's sort of like verging on, is this actually a human or is it a robot? Certainly better than like the whatever 1990s or 80s Steve Jobs "Hello World, I'm Lisa" presentation. And then here's like probably like the most modern model. It's also from a group within Google, and it's called Tacotron.
The buses aren't the problem. They actually provide a solution.
Yeah, so this one, like, it has some pretty noticeable artifacts, but one of the cool things is that what you might have noticed was that the words problem and solution were stressed, and in the text sentence, these words were actually, they appeared in all caps. So the model actually learned to sort of stress certain words based on what it's seen in the past. And hopefully I can get back to my presentation. Perfect, yeah. All right. So yeah, so text-to-speech, it's in pretty good shape right now, but my project that I wanted to work on was take speech from one person and convert it so it sounds like it was spoken by another person. And so yeah, there are a few ways to do it. It would be really amazing if we can do this using like with the raw audio, but if we need to, we could also try doing things with the spectrograms. So yeah, you can sort of think about this as finding like some mapping from some speech X and convert it so it sounds like it was spoken from the domain Y. And I tried to do this using two models. One was CGAN, and it was sort of like a direct application. And then another was using the Tacotron model that we just heard and making a decent number of modifications. So for data, I used this CMU Arctic data set, which is, what they did was they took like 1,000 sentences or utterances in Project Gutenberg, and they had two speakers. One was a male, one was a female, and they had them say these 1,000 utterances, and they provided the data as like nice paired examples. And so for CGAN, CGAN stands for Speech Enhancement GAN, and it was originally designed to clean up speech, clean up noisy speech, and it's actually important to know what they started with. They had like raw, clean speech, and they like simply like took noise and added noise, like actually additively added noise to the input signal. And then they used this as their noisy speech, and so their goal was to just clean up the noisy input, so just the clean speech remained. and they had good results, and their generator is basically a convolutional autoencoder, and their discriminator is basically half of that model with a few modifications to actually make it a discriminator. And so when I was training this, I didn't actually use their proposed like training objectives. I did like one slight modification. So up here, this is like the typical least squares GAN discriminator objective, and this, besides this, is the typical like least squares GAN generator objective, and both of these are actually conditional GANs. They have this additional term over here, which is they have the noisy input, they pass it through the generator, and then they try to minimize this generated clean input with the ground truth value. And I actually think that this was pretty important in terms of like what led to their results. But unfortunately, because my utterances weren't completely perfectly paired, I got rid of this loss term. And when I trained it, what ended up happening was that the discriminator just learned way too well. And yeah, the generator just failed to learn anything. Yeah, so when the results came, they were not great. This is probably an exaggerated result. They weren't all this like egregious, but yeah, what you see here is like the male audio, and then it's passed through the generator, and then this is supposed to be the female audio, and then this is the actual ground truth equivalent, and so it's nowhere close. Yeah, so yeah, I think like probably like the biggest insight and takeaway was that like the utterances being perfectly aligned is actually like probably really important for this scenario. And then another thing that could be like leading to some of the issues is that speech is like a very complicated type of data, and like if you're just looking at like the raw audio, it's sort of like a hierarchy of like time series because you might have like certain frequencies that make up like a phoneme, and then like a bunch of phonemes that make up a word, and then like a bunch of words that make up a sentence. And so this is something that is rather difficult to model, and yeah, I think I'll touch more on this later. But so what I tried to do is make some adjustments, and I used like the cycle GAN sort of objective, and so I had 2 generators and 2 discriminators, and I had a cycle consistency loss. And unfortunately, when the generator isn't performing well, like when you add this cycle consistency loss, it's really easy for it to just try to have some input X get passed through, and then it outputs just X again. And then if the next generator also outputs X again, then it's back to where it started from. And this is exactly what the cycle consistency wants to do. And so, yeah, basically when G learns the identity, it like perfectly satisfies the cycle consistency loss, and then nothing interesting happens. And this is especially easy when there are skip connections which occur in the generator. So the input is like almost directly attached to the output. Yeah, so this actually just shows just that. This is the cycle consistency loss. It pretty much drops right to 0. And yeah, the discriminator also has no problem figuring out what's going on. So as like a last attempt, I tried to like get rid of the skip connection. So this is now just a straightforward like convolutional autoencoder, and it sort of works well for initially. It certainly is able to train for like a lot longer without anything like too terrible happening, but in the end it looks like the generator just is not able to like figure out what's happening in this scenario. So take 2. So I tried now doing like Tacotron GANs. So Tacotron is this text-to-speech model, and it's basically like a fancy sequence-to-sequence model. And so what I did is I said, okay, for the generator, just take in linear scale spectrograms and then output linear scale spectrograms. For the discriminator, just use the encoder part of this model, you know, obviously different parameters, and then just take the last layer and like attach this fully connected layer and then make it a discriminator. Unfortunately, the results were very similar to what happened with CGAN. So yeah, basically, I think this is actually like just a really tough problem to solve. there definitely needs to be like a lot of care required when you're just like formulating like the GAN objectives. And I think what we've seen so far in like a lot of literature and even like amongst our own projects is that GANs work a lot better as soon as like you start adding extra loss terms. So as soon as like you start supervising them a little bit more, they seem to like perform even better. So this is definitely something to consider when moving forward with this aspect of the project in the future. And then also, if you look at like current successful voice conversion projects, they usually use like really treated data where like the utterances and the phonemes are like perfectly aligned. And so I think this could also definitely help move this area forward. So this happened like, I sort of got these results about like in the midway point of this project, and I obviously just didn't stop working after that. So what I decided to do is just work on like Tacotron, because the implementation I was using was actually created by one of the members of the audience here, Ryan. yeah, there he is. Okay, yeah, he is like the most starred public repo of this implementation. It's really good. And it's cool that he did that because Google has some amazing results. Yeah, so good. We don't even know is it like a human or is it a robot. But like unfortunately, this model is like really complicated. I did like a parameter count last night, and there are like 8.5 million parameters. And when Google like demoed their results came from a model that was trained with 2 million parameters. And so to put this into perspective, we did like a sanity check on like a very small amount of data. Actually, this data is like so small, it was just one batch of data. And we trained this for about like 40,000 times, and a bunch of people have done this. There's sort of a community working on this specific project and on this implementation. And like in general, this can take, training this one small batch of data can take like 7 to 12 hours depending on what your hardware is to train. And this is only for 40,000 iterations. So yeah, it's definitely hard to like understand whether or not this implementation is working fully just because it takes such a long time to train. And then to make matters even more complicated, Google has like an internal data set that they didn't release when they actually released their samples. So yeah, despite that, I've made some progress while working on this system. Specifically, I've sort of explored some of the hyperparameters, and I found like a subset that actually like matches or gets very close to what the paper used and generates like pretty good results on the sanity check data. And then what I decided to do was create or change the model so it can be trained in a distributed setting. Because if the model can be trained distributedly, that means that we can probably get more more training steps in, which means that we can get closer to that 2 million number, which I think is going to be like a very important time step, if or a very important like stage of this project if we ever want to get anywhere near the level of results that Google has. So I created like, there are two versions of the model now, one that can be trained synchronously, one that's trained asynchronously. And I've been able to train this on a slightly larger subset of the data, and I've gotten up to about like 220,000 global steps while training asynchronously. And yeah, so I'll talk a little bit about those results. So before I start, I'm going to talk about like my setup and like what I chose to train on. So yeah, convention says let's use GPUs, but I did some like experiments on the sanity check data, and I said, okay, when I'm training on 4 GPUs, I get about like 1.6 batches per second. And these GPUs are certainly not cheap. In fact, Google doesn't offer, spot instances, that's the word I'm looking for, like Amazon. So you're paying the full price for these GPUs. And so this is like $3.50 an hour for these 4 GPUs. And so if you look at like how much money or how many batches $1 gets you, it gets you like 1,500 batches. And so if you look at CPUs, I did like just a little bit of an analysis. I said, okay, let's just take a 24 virtual CPU machine and let's look at the speed, and we get nowhere near as fast as the 4 GPUs. That's correct. But we're also nowhere near the cost. And so if you look at the efficiency of training on CPUs, you're about twice as efficient per dollar. So I said, whoa, what are we doing here? Let's get rid of GPUs and let's train on CPUs. And let's just not train on like one machine of CPUs. Let's train on 6 machines and 360 or 384 GPUs. So yeah, that was it was a pretty cool point of the project. Yeah, so like sort of like each row here like maybe represents the machine roughly. And so yeah, but when you train distributedly, it's actually nothing like when you're training on a single GPU. What'll happen is let's say you train asynchronously. Your training will go nice for a little bit. You'll minimize your loss, and then very quickly you'll notice that gradients become stale, and then updates are actually happening that are no longer relevant. And so you'll get some like wild oscillations, and then eventually your model's going to diverge so much that your loss will just like reach infinity. So yeah, you actually need to be careful. So what you can do when you're training asynchronously is you can do gradient clipping, and you could also try to like remove some stale gradients. Another thing you can do if you want to train across like a lot of machines is actually train synchronously. So this was a trial that was trained synchronously on like a lower number of machines. And unfortunately, you can't really see this here because of the resolution, but it just takes like a really long time to train synchronously. So I stuck with the asynchronous method. And yeah, so the results, they were not bad. It's actually like quite like inconclusive as to like what's happened because I ran out of cloud credits. But like if you actually look at the loss is being minimized. Unfortunately, because I like toned down the learning rate so much, it's just taking like a really long time to minimize this loss. But although I don't have like any great audio samples yet, when you listen to the audio samples, it actually sounds very similar to early samples from the sanity check data, and the sanity check ended up producing good samples. So I think that there is some promise with this method. But like just for next steps, I think that I just need to maybe like train more and then increase the learning rate. And then if possible, also just like start training on like the entire data set. So right now, the sanity check data works on like maybe like a very, very small sliver over here. And the way that the training is currently set up, I'm probably using data from here to here. So I'm ignoring all of, sorry, this x-axis is like sequence lengths. So I'm ignoring all sequence lengths past 100. And so this is the CDF of this distribution. This is about 40% of the data that I'm currently training on. So yeah, thank you for listening to my presentation. You can find my work on my GitHub for the Tacotron right now, and for my like cycle GAN or sort of like speech synthesis GANs, you can find it on the MLJejuCamp page. Specifically, I want to thank like my mentor. This is me and my mentor at Hollow Mountain, and then everyone here at MLJejuCamp and Google Cloud for providing me with cloud credits. Thanks. Yeah.
Have you tried any other kinds of spectrograms rather than just linear scale spectrograms?
Okay. So yeah, so that's sort of interesting. And Tacotron, there's actually like Mulc scale spectrograms as part of the loss. So yeah, so it does get trained on both of those. But can you be a little bit more specific in your question? Like which part of the model are you talking about? Sorry, I've discussed a lot.
For the inputs, and also for the outputs.
Yeah, for the GANs. Yeah, okay. That's something I've been meaning to try, but I haven't tried that yet. Yeah.
Okay.
Do you have another question? Do you have any sample audio?
Yeah. So I have some like sanity check stuff, and I have like the current stage of the long training. Yeah. Let's see if I can.
Make it more fun.
Yeah. Sure. So this is the sanity check data, and this is data that the model was trained on after about like 49,000 steps.
The Lord spoke to Moses, saying,
Yeah, so it's able to generate something, certainly not anywhere near as good as the paper. And then in terms of, let's see, so for like the 220,000 or 100,000 global steps, we get something, but like it's arguably not even speech. Like it might be one phoneme at the end. Yeah, there might have been like something that it was trying to say. But this is actually like what it sounds like very early on in the sanity check. So I think this could be promising. I was actually looking at like there's another guy on GitHub who's publicly working on his own implementation, and he trained his for like 200 or like pretty much around the same length, and he has much better results. So I'm going to look more into like his hyperparameters and see what's going on. Yeah.
I haven't really looked into the Cybertron implementation, but since you have a much more noisier data set, so it'll be kind of redundant to add noise, have you tried any alignment methods like connectionist temporal classification alignment?
Wait, so what do you mean about like the noisy data set? Sorry.
So you've got your target pairs, but as you said, they're kind of misaligned compared to the very clean data sets that are.
Oh, yeah.
Have you tried any models that intentionally align them, like safety data and will be?
Okay, yeah, that's a pretty good question. No, I have not tried them yet, but yeah, can you actually follow up with me? I would like to write these things down.
Do you have any ideas from them?
Yeah, I'm not really too sure. I think like Ryan's also been working on noise conversion, so like he's pointed me to some directions for like other papers. I'm still like sort of looking more into it. Yeah, so sort of like the second half of this project, I just decided this is probably like too ambitious for this month, and so it'd be better just to get started with this text-to-speech portion. All right, thank you.
Thank you so much for your